Okay, let's wrap up chapter 3 here. The last rock group that we have not covered are the metamorphic rocks. So metamorphic rocks, like sedimentary rocks, are formed from pre-existing rock. They have to be there in the first place because to metamorphosize means to change form. So we're going to alter the mineral structure of pre-existing rocks, and that's what metamorphosizes them. There you go, there's the definition of metamorphism again. Now, the chemical composition of a rock changes because of heat and pressure usually. Now there can be a couple of extra agents that factor in, but most commonly it is this. Now, we're not necessarily, although there's an exception to this, let's say we have some rock in the earth and it's just sitting there. Boom, here we go, here's our rock. Now, when we say we're gonna alter the chemical composition, well, we're not gonna take new materials and necessarily dump them into the rock. That can happen, but that's sort of an exception. Really, what happens with metamorphism is we just add huge amounts of pressure, and that forces the minerals that are already there to rearrange in a different way. Or with the pressure, you basically can't have pressure without also having heat. So we can bake the minerals in here and cause them to alter too. We learned a little bit about this when we talked about how minerals are formed, because heat and pressure is one of the ways in which minerals are created. So I've used the cake baking, we call it metaphor, about 1,000 times, but it's a good one because when you have a cake, before it's baked, you have the egg, the flour, everything sitting there, but they're all still separate from each other. So if you just leave them sit there forever, it's not what you would call a cake. It's just like raw ingredients. So we can think of each of the ingredients as like the minerals in a pre-existing rock that's already there. If we bake it though, if we add all that heat, energy, then what we pull out, it's not accurate to say that there's still raw egg in your finished cake. And it's really not accurate to say that there's raw flour in there. The molecules, the atoms that were in the egg and the flour and all that are still present, but they've been rearranged in a way that we can no longer say they are what they used to be. And that's metamorphic rock as well. And virtually all metamorphism happens several kilometers below ground, because that's the only place where these kinds of pressures and temperatures exist. Now, although deep down here the rock may be subject to thousands of degrees of temperature changes, it doesn't melt, because if it did, it would be igneous rock. Most rocks, their melting point on the surface is not thousands of degrees. So how come they don't melt down there? Well, the pressure, the squeezing of all the weight of the earth above it keeps them from being able to, the molecules from being able to flow like a fluid does. So they're hot enough to melt, but the pressure won't allow it. Anyways, I've already said that existing minerals rearrange. So one type of metamorphism is contact metamorphism. This is when the source of the heat is magma deep below the earth. Now the magma sort of acts like the coils in our oven. It produces the heat that causes the change in the rocks. We're not saying that the metamorphic rock comes from the magma, because that's igneous rock, but it burns, it alters the rock around it. So, and there are stages of metamorphism too. Metamorphic rocks are like Pokemon. There are different levels to them, sort of. So if we take limestone that's been unaltered below Earth's surface, limestone is a sedimentary rock. It's a chemical, biological sedimentary rock even. But limestone can be metamorphosized into many different metamorphic rocks. With the least amount of heat added, it turns into marble. The statue of David is made out of marble. Countertops maybe at your home are made out of marble. And here's our magma source, so we're going to get closer to it. With more heat, calcite, chlorite, and serpentine minerals can be formed. I have some rock samples of those that I can show you. Even closer, deeper, nearer to the source of the heat, we get minerals like diopside and garnet. Garnet is a fairly precious gemstone, so like diamonds as well. Diamonds can only form with really close to a source of intense heat and lots of pressure. So here we can see a pretty rare glimpse of contact metamorphism happening. Now this black rock right here is igneous rock. Magma worked its way into a crack and solidified there. But if you look on either side of it, here's the very light tan colored rock. We don't know what kind it is, but it's there. You can see that this rock has been metamorphosized. It's been burned. It's a much darker color. So the mineral structure has no doubt been changed by that. And that's contact metamorphism. Now, contact metamorphism does not produce nearly as much rock as regional metamorphism. This is from plate boundaries. So when two plates collide with each other, or just simply the pressure from being underneath huge quantities of rock above you, this produces the pressure, and with that pressure also comes heat that metamorphosizes rocks. Getting back to the different stages, if rock is allowed to sit for long periods of time, it may go through these different stages. So shale is a sedimentary rock. It's nothing but compressed mud. So shale is pretty brittle. If you pick it up, you can break it just with your hands. But shale will morph into slate. Slate is a metamorphic rock. If any of you have a pool table at home or have tried to pick up a pool table, they're incredibly heavy. What pool tables do is a lot of them use a big slab of slate, this metamorphic rock, because it's made of compressed mud, it can be fairly easily be broken into layers. So if you're trying to build a pool table, that's what you want, because you want it to be flat. So you can break it into big flat rectangles, and then when they polish it, there's really no danger of it cracking down, because it's like plywood. Plywood is really strong against the layers, but with the layers it's fairly brittle, so they can polish that really easy. But anyways, slate can be metamorphosized even further into a rock called phyllite, and then schist, and then this is actually pronounced gneiss. That's the hardest, the most metamorphosized, takes the longest amount of time of that group of rocks. So here's the undeformed strata, and then here's what it may look like after regional metamorphism has taken over. And here are all those different rocks we talked about. What's kind of interesting here is what we're seeing is, you can think of it like mixing paint, but in reverse. So this shale, this sedimentary rock, this is where it starts. Now that is going to be composed of several different kinds of minerals. Now if you're mixing white and black paint, if you do a 50-50 mix, it's going to just be black. It's not going to be halfway between white and black. You're going to just barely make the black any lighter at all. So that's why the shale looks like that. What's happening as this is metamorphosized is the dark colored minerals and the light colored minerals in the shale, they're totally set. They're evenly mixed throughout, which is why it just looks very, very dark. But as it's metamorphosized, those minerals are forced to separate from each other. So look at how much lighter the slate looks, and then the phyllite looks a little lighter. When we get to schist, it starts to get a marbled appearance, kind of like granite, where you can distinguish between the different minerals. And then when we get to gneiss, it has become what we say foliated. You can see the bands. Here's a dark band, here's a light band, here's a dark band, a light band. So they've been pulled apart. Okay. The primary causes of metamorphism are heat and pressure. Now, what also happens with metamorphic rock is as it's metamorphosized, when it's cooked or baked under those extreme temperatures and pressures, it's also tempered or hardened by that process. It becomes resistant to those new temperatures. Because if it's made under many couple hundred of degrees temperatures, it will be resistant to those temperatures. Makes sense. Two or more minerals can come together to form new mineral structures inside the rock. That's what actually happens with garnet. So these garnet gemstones that are embedded in here, at one point, this would have been another type of rock. I'm not sure what kind, but it would have had no gemstones in it. Everything would have been mixed all evenly, like the schist was, or sorry, like the shale was. But metamorphism draws out those minerals or forces them to, sometimes it kind of does the opposite of what we saw in that picture. This is where it's forcing minerals to combine that could not combine under the original circumstances. So this is actually the exact opposite of that picture. And that's what makes these garnet gemstones here. Now here's the one where it's different. Hydrothermal solution, which is another mineral forming process, metamorphosizes rock. And it does that because it changes the mineral structure. So picture we'll just picture that this is a section of Earth's crust right here. So to show you that this is the surface, let's draw a house. Why not? There. So under here, it's all magma and stuff like that. This is Earth's mantle. Now, below the surface of the Earth, embedded in the crust, actually there's lots of water. And that water, as it sits down here, may be laced with large amounts of heavy metals. Well, the heat radiating upward forces that water up, and Earth's lithosphere, Earth's crust, obviously this is not drawn to scale, is full of cracks all throughout it. So this superheated water that is drawn upward because it's hot, mixed with its precious metals or whatever, works its way into those cracks. Oops. And then as it hardens, it leaves behind those metals. So we have a rock that had no silver, gold, uranium, whatever it happens to be, embedded in it. And then after this hydrothermal event, it now does. So really, we haven't exactly altered the whole structure of the rock. It's like, what's the difference between a regular cookie and the exact same cookie but with chocolate chips in it? Well, the only difference is the chocolate chips. We haven't changed the fundamental structure of the rest of the thing, but technically it's metamorphism. And then lastly, well, this is actually how metamorphic rock is classified. It's just by its outward appearance, so it's really easy. Foliated metamorphic rocks have distinct bands, and we kind of went over this process. It's formed, it is the result of the different types of minerals either combining into new types or being forced to separate from each other. So this is what gneiss looks like, I believe. So you can see there's dark and light bands here. It's been foliated. Non-foliated metamorphic rock, it just simply doesn't have any distinct bands. Usually there's only one type of mineral. Limestone, as it's converted into marble, it does look a little bit different, but it's definitely not foliated. And there, I guess it's just an example. So this is a piece of slate. This is the metamorphosized mud.
Hi.
Hi.